Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The world of mathematics frequently presents problems that, while seemingly esoteric, possess profound implications for our understanding of the universe. Among these, the Poincaré Conjecture stood for a century as a tantalizing challenge, a Gordian knot in the field of topology. Its resolution by Grigori Perelman in the early 2000s marked a watershed moment, a triumph of ingenuity and perseverance that resonated far beyond the hallowed halls of academia. The conjecture, posed by Henry Poincaré in 1904, concerns the fundamental shapes of three-dimensional spaces. Topology, at its heart, studies properties of spaces that remain unchanged under continuous deformations, such as stretching, bending, or twisting, without tearing or bluing. Imagine a coffee mug molded from clay. A topologist views it as fundamentally the same as a donut, since one can be smoothly deformed into the other. The Poincaré conjecture sought to extend this type of reasoning to higher dimensions, specifically to characterize the three-dimensional sphere, the surface of a ball generalized to one dimension higher. Poincaré's initial formulation involved a seemingly simple question: is every simply connected, closed three-dimensional manifold topologically equivalent to the three-dimensional sphere? A manifold, in this context, is a space that locally resembles Euclidean space. Closed means it is compact and has edges. Simply connected means that any loop within the manifold can be continuously shrunk to a point. The conjecture proposed that if a three-dimensional manifold possesses these properties, it must be topologically the same as a three-dimensional sphere. The importance of the Poincaré conjecture lay in its potential to unlock deeper insights into the classification of three-dimensional manifolds. These manifolds are fundamental building blocks in topology and geometry, appearing in various areas of mathematics and theoretical physics, including cosmology and string theory. A complete understanding of their properties would have far-reaching consequences. Prior to Perelman's work, numerous mathematicians had grappled with the conjecture, devising ingenious approaches that ultimately fell short. The problem proved to be remarkably resistant to attack, with proposed solutions often containing subtle flaws or relying on unproven assumptions. The difficulty stemmed from the inherent complexity of three-dimensional topology and the challenge of finding suitable tools to analyze these spaces. Perelman's approach, a radical departure from previous attempts, involved the use of Ricci flow, a concept introduced by Richard Hamilton in the early 1980s. Ricci flow, analogous to the diffusion of heat, describes how the geometry of a manifold evolves over time. In essence, it smooths out the curvature of the manifold, attempting to make it more uniform. Hamilton hoped that by applying Ricci flow to a three-dimensional manifold, it would eventually deform into a simpler, more manageable shape, perhaps even the three-dimensional sphere. However, a significant obstacle arose: singularities. As Ricci flow progresses, regions of high curvature can develop, leading to points where the flow breaks down. These singularities represent a major hurdle, preventing the flow from reaching a smooth, uniform state. Overcoming this hurdle required innovative techniques to control and manage the formation of singularities. Perelman's groundbreaking contribution lay in his development of a method to handle these singularities, a process he termed Ricci flow with surgery. This involved carefully cutting the manifold at singular regions and replacing them with simpler, well-understood pieces. By repeatedly applying Ricci flow and performing surgery, Perelman demonstrated that he could effectively decompose any simply connected, closed three-dimensional manifold into simpler components, ultimately proving the Poincaré conjecture. The challenges in making Ricci flow work for the Poincaré conjecture were substantial. The formation of singularities threatened to derail the entire process, leading to uncontrolled behavior and preventing any meaningful conclusions. Perelman's surgery technique had to be meticulously designed to ensure that the cutting and pasting operations preserved the essential topological properties of the manifold while eliminating the problematic singularities. This required a deep understanding of both Ricci flow and three-dimensional topology. Grigori Yakovlevich Perelman's path to solving one of mathematics' most enduring problems began in Leningrad, now St. Petersburg, Russia. Born in 1966. He displayed exceptional mathematical talent from a young age. He excelled in mathematics competitions, earning a gold medal at the International Mathematical Olympiad in 1982. Perelman pursued his mathematical studies at Leningrad State University, where he joined the research group of Alexander Alexandrov, a renowned geometer known for his work on spaces of curvature bounded from below. This early exposure to Alexandrov's ideas profoundly influenced Perelman's geometric intuition and provided him with a solid foundation for his later work on Ricci flow. Alexandrov's spaces of curvature bounded from below are generalizations of Riemannian manifolds that allow for singularities and corners. They provide a powerful framework for studying geometric objects with less regularity, than smooth manifolds. Perelman's work on Alexandrian spaces, published in the early 1990s, demonstrated his mastery of geometric analysis and his ability to handle complex geometric structures. This experience proved invaluable in his later work on Ricci flow, where he had to confront the challenge of singularities. The influence of Alexander Alexandrov on Perelman's mathematical development cannot be overstated. Alexandrov instilled in Perelman a deep appreciation for geometric intuition and a willingness to tackle challenging problems with unconventional approaches. His work on Alexandrov spaces provided Perelman with the tools and insights necessary to navigate the complexities of Ricci flow and singularity analysis. Alexandrov's mentorship shaped Perelman's mathematical worldview and prepared him for the monumental task of solving the Poincaré conjecture. The geometric insights gained from his work on Alexandrov spaces enabled him to develop the sophisticated surgery techniques that were essential to his proof. The focus on curvature and its behavior in singular spaces, a hallmark of Alexandrov's work, directly translated into Perelman's approach to handling singularities in Ricci flow. Perelman's earlier work on Alexandrov spaces proved invaluable in his later work on Ricci flow, where he had to confront the challenge of singularities. Alexandrov instilled in Perelman a deep appreciation for geometric intuition and a willingness to tackle challenging problems with unconventional approaches. His work on Alexandrov spaces provided Perelman with the tools and insights necessary to navigate the complexities of Ricci flow and singularity analysis. Alexandrov's mentorship shaped Perelman's mathematical worldview and prepared him for the monumental task of solving the Poincaré conjecture. The geometric insights gained from his work on Alexandrov spaces enabled him to develop the sophisticated surgery techniques that were essential to his proof. The focus on curvature and its behavior in singular spaces, a hallmark of Alexandrov's work, directly translated into Perelman's approach to handling singularities in Ricci flow. The resolution of the Poincaré conjecture, a century-old problem in topology, hinged on Perelman's ingenious application of Ricci flow with surgery. The Ricci flow, conceived by Richard Hamilton, acts as a geometric heat equation, evolving the metric of a Riemannian manifold over time. Analogous to how heat diffusion smooths temperature gradients, Ricci flow aims to smooth out the curvature of a manifold. Mathematically, the Ricci flow equation is expressed as the time derivative of the metric tensor g sub ij equals -2 times the Ricci tensor r sub ij. This equation describes how the metric changes at each point on the manifold over time, driven by the local curvature. The Ricci tensor, r sub ij, is itself a contraction of the Riemann curvature tensor, a more fundamental object that captures all the curvature information of the manifold. The Ricci tensor essentially measures the average sectional curvature at a point in each two-dimensional plane passing through that point. In essence, the Ricci flow attempts to redistribute curvature more evenly across the manifold. Regions of high positive curvature tend to shrink, while regions of high negative curvature tend to expand. The hope is that, as time progresses, the manifold will converge to a simpler, more uniform geometry. However, a significant obstacle arises: singularities. Under Ricci flow, certain regions of a manifold can develop infinite curvature in finite time, halting the flow's progress. These singularities represent points where the smoothing process breaks down. Imagine attempting to smooth a surface with a sharp, pointed cone. As the smoothing process continues, the tip of the cone becomes increasingly sharp, eventually leading to a singularity. Perelman's groundbreaking contribution was the development of Ricci flow with surgery, a method for continuing the Ricci flow past these singularities. The core idea involves identifying and excising singular regions, then carefully pasting the remaining pieces back together to create a new, slightly modified manifold. This process allows the Ricci flow to continue evolving, albeit on a sequence of manifolds that undergo surgery. The surgery process is delicate and requires precise control to ensure that the topology of the manifold does not change in undesirable ways. Perelman introduced several key innovations to manage this process. One crucial element is the concept of non-collapsing. A manifold is said to be non-collapsed if, at every point and at every scale, it contains a definite amount of volume. This condition ensures that the manifold does not pinch off and develop singularities that are too severe to handle. Perelman developed geometric inequalities to control the surgery process and ensure that the non-collapsing condition is maintained. One of his most important tools is the entropy functional, a quantity that measures the disorder or complexity of the manifold. Perelman demonstrated that the entropy functional increases along the Ricci flow, providing a measure of the flow's progress towards a simpler geometry. Another key tool is the reduced volume, a quantity that is closely related to the entropy functional. Perelman showed that the reduced volume satisfies certain monotonicity properties along the Ricci flow, which allows him to control the size and shape of the singular regions that need to be excised. These inequalities provided the rigorous foundation for his surgery techniques. To illustrate the surgery process in a simplified setting, consider a dumbbell-shaped manifold consisting of two spheres connected by a thin tube. As Ricci flow evolves this manifold, the tube will tend to shrink, while the spheres will tend to become more round. Eventually, the tube may collapse to a singularity, pinching off the two spheres. In Perelman's surgery process, one would identify this collapsing region and excise it, effectively cutting the dumbbell into two separate spheres. Then, one would cap off the resulting holes with spherical caps, creating two complete spheres. This surgery process removes the singularity and allows the Ricci flow to continue evolving on the two separate spheres. The actual surgery process in Perelman's proof is far more complex, involving intricate geometric analysis and careful control of the curvature and topology of the manifold. However, the basic idea remains the same: identify and excise singular regions, then carefully paste the remaining pieces back together to continue the Ricci flow. Perelman's meticulous control of the surgery process, guided by his entropy functional and reduced volume estimates, allowed him to demonstrate that the Ricci flow with surgery eventually leads to a decomposition of the manifold into simpler pieces. In the case of the Poincaré conjecture, he showed that any simply connected, closed three-manifold will eventually become a round three-sphere under Ricci flow with surgery, thus proving the conjecture. Perelman's work on Ricci flow with surgery was deeply influenced by Richard Hamilton's original ideas on Ricci flow. Hamilton laid the groundwork for the entire field, and Perelman built upon Hamilton's work in a profound way. Additionally, Perelman's deep understanding of geometric analysis, honed through his earlier work on Alexandrov spaces, was essential to his success. Xintang Yao's work on geometric analysis also provided important tools and techniques that Perelman utilized in his proof. The impact of Perelman's work on subsequent mathematicians has been immense. His techniques for handling singularities in Ricci flow have opened up new avenues of research in geometric flows and related problems. Numerous mathematicians were actively working on extending and generalizing Perelman's results to other geometric settings. His ideas have provided a powerful framework for understanding the geometry and topology of manifolds, and his work continues to inspire mathematicians around the world. Perelman's progress on Ricci flow with surgery provided the instruments required to address a problem of even greater scope of Thurston's geometrization conjecture. This conjecture, formulated by William Thurston in the 1970s, represents a powerful attempt to classify all three-dimensional manifolds. Thurston's vision proposed that every compact, orientable three-manifold could be decomposed in a canonical way into pieces, each of which possesses one of 8 specific geometric structures. To understand the profundity of this statement, one must appreciate the challenge of classifying manifolds in general. While two-dimensional manifolds are fully classified by their genus, the number of holes, the landscape of three manifolds is vastly more intricate. Thurston's conjecture offered a way to bring order to this complexity by suggesting a fundamental structural principle. The core idea is that a three-manifold, however convoluted its initial appearance, can be systematically cut along certain surfaces until the resulting pieces are geometrically pure. These pure pieces are then modeled on one of 8 possible geometries, each a homogeneous Riemannian manifold. These 8 Thurston geometries are three-dimensional Euclidean space, the three-sphere, three-dimensional hyperbolic space, the product of the real line, and the two-sphere, the product of the real line and the hyperbolic plane, the universal cover of the special linear group of degree 2 with real entries, the nil geometry, and the solva geometry. The Euclidean geometry is simply ordinary flat three-dimensional space. The three-sphere is the set of points in four-dimensional space at a fixed distance from the origin, inheriting a natural metric from the ambient space. Three-dimensional hyperbolic space is a negatively curved analog of Euclidean space, exhibiting constant negative curvature. The remaining 5 geometries are more exotic, possessing less symmetry than the first 3. The geometrization conjecture asserts that every compact, orientable three-manifold admits a decomposition into pieces that are geometrically uniformized in this way. This is analogous to the uniformization theorem for Riemann surfaces, two-dimensional manifolds, which states that every Riemann surface admits a metric of constant curvature, making it either spherical, Euclidean, or hyperbolic. Thurston's conjecture extends this idea to one higher dimension, positing a similar kind of geometric simplification. Perelman's work on Ricci flow with surgery entered this picture as a potential means of realizing Thurston's vision. Ricci flow, as developed by Richard Hamilton, provides a way to deform the metric of a manifold in a way that tends to smooth out its curvature. The surgery process, introduced by Perelman, allows one to excise singular regions that develop during the flow and replace them with simpler topological structures. The challenge in extending Ricci flow with surgery to prove the geometrization conjecture lay in demonstrating that this process would indeed lead to a geometric decomposition. The Ricci flow must be shown to evolve a given three-manifold in such a way that it eventually decomposes into pieces, each of which converges to one of the 8 Thurston geometries. The most difficult case to handle was that of hyperbolic pieces. Hyperbolic geometry exhibits constant negative curvature, and it was necessary to show that the Ricci flow, with appropriate surgeries, could evolve a manifold toward this state. Perelman's analysis involved a deep study of the behavior of Ricci flow near singularities. He developed sophisticated techniques for controlling the formation of singularities and for performing surgeries in a way that preserves the overall topology of the manifold. His work demonstrated that the Ricci flow with surgery process does indeed lead to a geometric decomposition, thereby proving Thurston's geometrization conjecture. A simple example of a three-manifold that admits a geometric decomposition is the connected sum of two lens spaces. A lens space is a three-manifold obtained by gluing together two solid tori along their boundaries. The connected sum of two manifolds is formed by removing a small ball from each manifold and then gluing the resulting boundaries together. The connected sum of two lens spaces decomposes into two pieces, each of which admits a spherical geometry. The influence of Thurston's ideas on Perelman's work is undeniable. Thurston's geometrization conjecture provided the overarching goal that Perelman's work on Ricci flow with surgery ultimately achieved. Thurston's vision of geometric topology shaped the direction of Perelman's research and provided a framework for understanding the structure of three manifolds. The geometrization theorem has extensive consequences in topology and geometry. It provides a fundamental understanding of the structure of three manifolds, revealing that they are built from a small number of basic geometric building blocks. This theorem has led to new insights into the classification of three manifolds and has opened up new avenues of research in geometric topology. The impact of Perelman's work on subsequent mathematicians has been immense. His techniques for handling singularities in Ricci flow have opened up new avenues of research in geometric flows and related problems. Numerous mathematicians are actively working on extending and generalizing Perelman's results to other geometric settings. His ideas have provided a powerful framework for understanding the geometry and topology of manifolds, and his work continues to inspire mathematicians around the world. Perelman's proof of the geometrization conjecture was a landmark achievement in mathematics, solving a problem that had been open for decades. His work has transformed our understanding of the structure of three manifolds and has provided a powerful tool for studying their geometry and topology. This achievement solidified his place as one of the most influential mathematicians of the 21st century. Topologists studying three manifolds and geometric structures have benefited immensely from Perelman's work, gaining powerful tools and insights for their research. His work on Ricci flow with surgery was deeply influenced by Richard Hamilton's original ideas on Ricci flow. Hamilton laid the groundwork for the entire field, and Perelman built upon Hamilton's work in a profound way. Additionally, Perelman's deep understanding of geometric analysis, honed through his earlier work on Alexandrov spaces, was essential to his success. Xingtong Yao's work on geometric analysis also provided important tools and techniques that Perelman utilized in his proof. Perelman's proof of the Poincaré conjecture and geometrization conjecture represents a landmark achievement in mathematics, solving a problem that had been open for decades. His work has transformed our understanding of the structure of three manifolds and has provided a powerful tool for studying their geometry and topology. This achievement solidified his place as one of the most influential mathematicians of the 21st century. Topologists studying three manifolds and geometric structures have benefited immensely from Perelman's work, gaining powerful tools and insights for their research. His work on Ricci flow with surgery was deeply influenced by Richard Hamilton's original ideas on Ricci flow. Hamilton laid the groundwork for the entire field, and Perelman built upon Hamilton's work in a profound way. Additionally, Perelman's deep understanding of geometric analysis, honed through his earlier work on Alexandrov spaces, was essential to his success. Xingtong Yao's work on geometric analysis also provided important tools and techniques that Perelman utilized in his proof. A key innovation in Perelman's work lies in his ingenious application of comparison geometry. Comparison geometry provides a way to understand the curvature of a space by comparing it to spaces with known curvature, such as Euclidean space or hyperbolic space. Perelman employed comparison theorems to control the behavior of the Ricci flow, specifically to show that singularities, points where the curvature becomes infinite, form in a controlled manner. He showed that these singularities, rather than being chaotic and unpredictable, can be understood and surgically removed. This involved developing precise estimates on the geometry near these singularities, allowing him to perform surgeries that cut out the singular regions and replace them with smoother geometry. Specifically, Perelman introduced a reduced volume functional, which is a measure of the size of a manifold that is invariant under certain transformations. By studying how this functional changes under the Ricci flow, he was able to obtain crucial estimates on the geometry of the manifold. This involved intricate analysis of differential inequalities and the development of new techniques for studying the evolution of geometric quantities under the Ricci flow. For instance, Perelman's non-collapsing theorem, a central result in his work, states that at a certain scale, the manifold does collapse to a lower dimensional space. This theorem relied heavily on comparison geometry arguments and the careful analysis of the reduced volume functional. Another crucial aspect of Perelman's work is his development of gradient estimates for solutions to certain parabolic equations. These estimates provide bounds on the rate of change of solutions, which are essential for controlling the behavior of the Ricci flow. He derived these estimates by cleverly exploiting the maximum principle, a powerful tool in the theory of partial differential equations. The maximum principle states that the maximum value of a solution to a certain type of equation occurs on the boundary of the domain. Perelman used this principle to obtain pointwise estimates on the solutions, which in turn gave him the desired gradient estimates. His introduction of entropy functionals played a decisive role. Entropy functionals are mathematical quantities that measure the disorder or randomness of a system. Perelman introduced a specific entropy functional tailored to the Ricci flow, and he showed that this functional is monotone decreasing under the flow. This monotonicity property provided a powerful tool for analyzing the long-time behavior of the Ricci flow and for proving convergence results. The entropy functional can be expressed as the integral over the manifold of a certain expression involving the curvature and its derivatives. The fact that this integral decreases under the Ricci flow provides a strong constraint on the evolution of the geometry. The lasting impact of Perelman's work on the field of geometric analysis and topology is profound. His techniques have become standard tools for studying geometric flows and related problems. His ideas have inspired new research in areas such as machine learning and computer vision, where geometric methods are increasingly being used to analyze complex data sets. Future generations of mathematicians studying geometric analysis and topology will undoubtedly find Perelman's work to be a rich source of inspiration and guidance. Perelman's contributions are of immense significance within the context of 20th and 21st century mathematics. The Poincaré Conjecture, posed in 1904, stood as one of the most important unsolved problems in topology for a century. Its resolution by Perelman marked a monumental achievement. Furthermore, his proof of the geometrization conjecture, a far-reaching generalization of the Poincaré conjecture, provided a complete classification of three manifolds, answering fundamental questions about their structure. This breakthrough has had a transformative impact on the field, providing a new framework for understanding the geometry and topology of these spaces. Beyond the specific results he proved, Perelman's work introduced new ideas and techniques that have had a lasting influence on mathematics. His use of comparison geometry, gradient estimates, and entropy functionals has opened up new avenues of research and has led to significant progress in related areas. His work has also highlighted the deep connections between geometry, analysis, and topology, fostering a more unified approach to these fields. The ethical and epistemological implications of Perelman's decision to refuse the Fields Medal and Millennium Prize are complex and multifaceted. His refusal can be interpreted as a critique of the mathematical establishment and its reward system, which he may have perceived as being overly focused on individual recognition and competition. He seemed to value the pursuit of knowledge for its own sake, rather than for the accolades and rewards it might bring. His actions raise important questions about the nature of mathematical discovery and the role of collaboration in scientific progress. While he built upon the work of others, particularly Richard Hamilton, he felt that his own contributions were significant enough to warrant independent recognition. His decision to decline the prizes also highlights the tension between individual achievement and the collective nature of mathematical knowledge. In conclusion, Grigori Perelman's intellectual journey and lasting legacy are marked by profound insights, groundbreaking techniques, and a complex relationship with the mathematical community. His proof of the Poincaré conjecture and geometrization conjecture represents a monumental achievement in mathematics, transforming our understanding of the universe's geometric structure. His work on Ricci flow with surgery has provided a powerful tool for studying the geometry and topology of ring manifolds, and his techniques continue to inspire and inform contemporary research. The enduring importance of Perelman's contributions to geometric topology and analysis is undeniable. His introduction of comparison geometry, gradient estimates, and entropy functionals has opened up new avenues of research and has led to significant progress in related areas. His work has also highlighted the deep connections between geometry, analysis, and topology, fostering a more unified approach to these fields. The long-term significance of his work lies in its potential for future applications. Geometric methods are increasingly being used in areas such as machine learning, computer vision, and materials science. Perelman's techniques may provide valuable tools for tackling complex problems in these fields, leading to new discoveries and innovations. His legacy extends far beyond the realm of pure mathematics, with the potential to impact a wide range of scientific and technological endeavors.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.